Now this video deals with the topic of factorization, the factorization of expressions. But before we delve into the actual factorization technique, we need to understand or remind ourselves of how to determine the highest common factor of a set of two or more terms. The highest common factor, also known as the HCF, is something you've met before, probably in primary school, if not in junior secondary school, and it's determined as follows. So if you have two or more terms, one expresses each term as a product of its prime factors and its variables, if it has variables, and one then determines the product of the common factors. The product of these common factors is the highest common factor. What is a prime factor? Well, let's even start with prime numbers. What is a prime number? A prime number is a number which is only divisible without a remainder by itself and 1. And prime numbers include 2, 3, 5, 7, 11, and there's more, 13, and so on. So this is something you've met before. So we're not going to dwell too much on this. A factor of a number or a term is a divisor of that term which gives no remainder. So for instance, for 4, it has a factor of 2 because 4 divided by 2 is 2. There's no remainder. 4 is also a factor of 4 because 4 divided by 4 is 1. The factors of 6 are 2, 3, and 6. Each of these terms are divisors which, when 6 is divided by them, result in an answer with no remainder. So 6 divided by 2 is 3, 6 divided by 3 is 2, 6 divided by 6 is 1. There's no remainder when you carry out the division. For example, if you divided 6 by 5, you would have 1 remainder 1. But 6 divided by 2 just gives 3. There's no remainder. Remainder of 0 or no remainder. So that's what a factor is. So let's go for another one. The number 9 has factors of 3 and 9. 9 divided by 3 is 3. 9 divided by 9 is 1. And that's it for factors. In order to determine the HCF of two or more numbers, each of these numbers have to be broken down into a product of their prime factors. So what we're going to do now is just focus on breaking down numbers into products of prime factors. So let's take, for example, number 9. This number has factors 3 and 9. Of these factors, only 3 is a prime number. So in order to break down 9 to a product of its prime factors, it has to be broken down into a product of numbers involving just 3, because 3 is the only prime factor. So 9, as we know, is 3 times 3. Here we have 9 as a product of its prime factors. 3 is a factor of 9 and it's also a prime number. So 3 is a prime factor of 9. 3 times 3 is 9. Here's another example, 6. 6 is 2 times 3. 2 is a factor of 6 and is also a prime number. 3 is a factor of 6 and is also a prime number. 2 times 3 is 6. So 6 is broken down into a product of its prime factors. Here's another one, 14. 14 is 2 times 7. 2 is a factor of 14. 7 is a factor of 14. 2 and 7 are also prime numbers. So 2 and 7 are prime factors of 14. 2 times 7 is 14. So 14 here has been written as a product of its prime factors. Let's take a last example, the number 10. Expressing this as a product of its prime factors, well, let's consider the factors of 10. The factors of 10 are 2, 5, and 10. All these numbers are divisors of 10 that leave no remainder when 10 is divided by any of them. Which ones of these are prime? 2 is a prime number and 5 is a prime number, as you can see here. So 2 and 5 are prime numbers, and they're also factors of 10. Therefore, 2 and 5 are prime factors of 10. So let's try and form 10 using 2 and 5. Well, 10 is actually 2 times 5. So 10 as a product of two prime factors is 2 times 5. So this is an elementary concept that you need to factorize expressions. And this is primary school stuff. So this is essentially a revision session. Here's an example question. And it requires us to find the HCF of the following two numbers. To find the HCF of two numbers, the numbers have to be expressed as product of their prime factors, and then the HCF is the product of the common factors of the two numbers. So, for instance, 16 has a product of its prime factors. What are the factors of 16? Factors of 16 are 2, 4, 8, and 16. So 16 has a product of its prime factors though. Out of all these factors, which of them are prime? Just 2. Only 2 is a prime number here. So 16 can be written as 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. 4, similarly, is 2 times 2. 4 only has the following factors: 2 and 4. Only 2 is prime, so 2 times 2 is 4. What are the common factors? Well, 2 is a common factor, and another 2 is a common factor. So the HCF is a product of the common factors 2 and 2. 2 times 2 is a common factor. The common factor is 4. So the HCF is 4. So the HCF of 16 and 4 is 4. Here's another example. We're required to find the HCF, the highest common factor of 16x and 4x. So in order to do this, you need to express each of these terms as products of their prime factors and their variables. In this case, we have variables. So let's just first write this as 16 times x and 4 times x. Now let's break down 16 into a product of its prime factors, and let's break down 4 into a product of its prime factors. And we just did that. 16 is 2 times 2 times 2 times 2. Then we have that's 16, then times x. 4 is 2 times 2, 2 times 2, and times x. So in terms of their common factors, we have 2, one set of 2s. So 2 is here and 2 is here, so it's a common factor. We have 2 here and 2 here. It's also a common factor. We have x here and x here, so it's also a common factor of these two terms. The HCF, therefore, of these two terms is the product of all the common factors. So it's 2 times 2 times x, which is 4x. So the HCF of 16x and 4x is 4x. Here's another example. Find the highest common factor of 3a and 6a. So these terms involve variables. So in order to do that, we need to express the terms as product of their prime factors and variables. Here we have 3a, which is 3 times a. And we have 6a, which is 6 times a. So now let's see if we can break this down further. 3 is a prime number, so we have nothing to change here, because now 3a is a product of its prime factors and a. 3 is a prime number, so its prime factor will be 3. So there's nothing to do here. 6, however, is not a prime number and has the factors 2 and 3. 2, 3, and 6. Of these factors, only 2 and 3 are prime numbers. So therefore, only 2 and 3 are prime factors of 6. So we need to try and form 6 using 2 and 3. So we need to express 6 as a product of any two of its prime factors. So doing so here gives, well, in this case, 3 times a remains as 3 times a. 3 times a is an expression of 3a as a product of its prime factors and variables. The only variable here is a. 6a, 6 times a, the same thing as 2 times 3 times a. This 6 here has been expressed as a product of its prime factors. A, the variable, just remains itself here. Now, the common factors are 3 and A. So the HCF of 3A and 6A is given by the product of the common factors. It's given by 3 times A, which is 3A. Now here's a slightly more challenging example. We're required to find the HCF of the following terms: 2x squared y and 3xy. So let's write them out as product of their prime factors and the variables. Now 2x squared y is 2 times x times x. So x squared is x times y. 3xy is 3 times x times y. Now if we observe this right hand side expression, it is a product of the variables and a prime factor of 2. 2 has factors. 2 only has one factor itself, and 2 is a prime number, so 2 is a prime factor of 2. So there we go. Same thing for 3. 3 only has one factor, which is 3, and 3 is a prime number, so 3 is a prime factor of 3, and that's what we have here. So 3xy is a product of its prime factors and the variables. 2x squared y is here has been written as a product of its prime factors and its variables. So let's look for common factors. Well, we have an x here and we have a y here. So the common factors are x and y. Therefore, the HCF is x times y, the product of the common factors, which is x, y. Now that you understand how to determine the highest common factor of two or more terms, you will find that factorizing a given expression is a piece of cake. In order to factorize an expression, one has to divide that expression through by its HCF and then multiply the result by the HCF. So in essence, in order to factorize an expression, all you need to know is its HCF, and you then divide the expression by the HCF and multiply the result by the HCF. It's as simple as that. So in mathematics, an expression is simply a symbol or a bunch of symbols that has a value, really. So for instance, you can have 2x, the term 2x is an expression. 2x plus 4y is an expression. X plus 2, everything raised to the power of 2 is an expression. All these kind of terms, these symbols, a bunch of symbols, are expressions in maths, but that's not the key thing. The key thing here is just to learn how to factorize these expressions, but you need to know what expressions are. But generally, you'll be given expressions and you'll be asked to factorize them, so you don't really need to worry about what expressions are. So here's an example. We need to factorize the expression given, which is ax plus ay plus az. But in order to factorize an expression, we need to divide the expression through by the HCF of its terms, and we need to multiply the result by the same HCF. So we need to know the HCF of this expression's terms. The terms are ax, ay, and az. Representing them as a product of their prime factors and variables is the next step. Now these terms just involve variables, so we just need to express each term as a product of the variables involved. So ax is the same thing as a times x, ay same thing as a times y, az is the same thing as a times z. They all have a common factor of a, so a is their only common factor. So the HCF is the product of all the common factors. Since there's only one common factor, the HCF is a. So the next step is to divide the expression through by the HCF. So we're going to divide it through by the HCF, which is a, and then multiplying the result obtained by the same HCF. And we're pretty much done, because all we have to do now is just divide. A here 1, 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 a here 1. So what we're left with in the bracket, x times 1, which is x divided by 1, is x, plus y times 1 over 1, which is y, plus 1 times z over 1, which is z, multiplied by a. So the result of the factorization of ax plus ay plus az is x plus y plus z times a, which is the same thing as a times x plus y plus z. Because we're multiplying two terms. We're multiplying this term and this term. And when an expression just involves the multiplication of in any number of terms, the order in which the multiplication is carried out does not matter. So we can say a times x plus y plus z. We can rearrange the order. So this is the result of the factorization. Here's another expression that needs to be factorized. Bx plus by plus ac. Now let's have a look at the common factors of the terms of these expressions. Now, bx as a product of its factors and its variables is b times x. It just involves variables. By is b times y. AC is a times c. So, and you notice that only these two terms have a common factor, b. X appears nowhere else, y appears nowhere else, a appears nowhere else, c appears nowhere else. So what do you do in a situation like this? Well, you say, I'm going to rewrite this expression as bx plus by plus ac. What you do is you group the terms that have a common factor, then you factorize just the terms, the expression involving the terms with the common factors. So in our case, we just focus on this expression and we factorize it. So we just focus on these two terms. We know they have a common factor of b, so their HCF is b, because that's the only common factor. So we divide this expression through by its common factor, and multiply by the same HCF. Sorry, you say you divide this expression through by its HCF and you multiply the result by the HCF. And then this AC term just remains unchanged. And doing so gives x plus y plus AC, because b here 1, b here 1, b here 1, b here 1. And we're just left with this. So this result, this expression, when factorized, is this. Here's another example. The given expression is 8x plus 2x squared, and we're required to factorize this expression. The first thing to do is determine the HCF of the terms within the expression. The expression has two terms, 8x and 2x squared. In order to determine the HCF, we have to express each term as a product of its prime factor. So 8x is 8 times x, and as a product of its prime factors and variables, 8x is 8 times x. 8 as a product of its prime factors is 2 times 2 times 2. As you know, 8 has factors 2, 4, and 8. Only 2 is a prime number, so only 2 is a prime factor of 8. So 8 as a product of its prime factor is 2 times 2 times 2, which gives 8. Then we have times x here. 2x squared is 2 times x times x. X squared is x times x. The common factors are 2 and x. So the HCF of these two terms is 2 times x, which is equal to 2x. Now to the final step. The original expression is divided through by the HCF So actually, let's do it this way. The original expression, this, is divided through by the HCF, which is 2x, and the result obtained is multiplied by the HCF. 8x over 2x is what? 2x squared over 2x is what? Well, I'm just going to carry out this simplification separately. Now, 8x over 2x is the same thing as 8 times x over 2 times x, which is the same thing as, this can be simplified as follows. X here, 1, x here, 1, 2 here, 1, 2 and 8, 4. So we have numerator as 4 times 1, which is 4, and 1 times 1, which is 1. 2x squared over 2x. 2x squared over 2x, same thing as 2 times x, or rather 2 times x squared over 2 times x. 2 here 1, 2 and 2 1. So we're left with 1 times x squared, 1 times x. And from one of the laws of indices, you know that x to the m over x to the n is equal to x to the m minus n. Therefore, x to the 2 over x to the 1 is x to the 2 minus 1, which is equal to x to the 1, which is equal to x. So what we have here is 2x times 8x over 2x, 4 over 1, which is 4, plus 2x squared over 2x. 2x squared over 2x is x. So the result is 2x into 4 plus x. That is the result of factorizing this expression. Now is a good point to mention that factorization can be considered as an inverse process to expansion, which we've met before. So we started with the expression 8x plus 2x squared. We factorized it, and we got 2x plus 4x. 2x times 4 plus x. Now, if you expand this expression, you go back to the original expression, as you see shortly. So when you expand this expression, what do you get? Well, you have the first term outside times the first term inside, which is 2x times 4, which is 8x. Then you note the sign after the first term inside. Then the first term outside minus the second term inside, 2x times x, which gives 2x squared, which is the original expression. So factorization can be considered as an inverse process to the expansion process. And after factorization, when you get your result, you can always test that the answer is right by expanding your answer. If you get the original expression when you expand your answer, like we did here, we expanded 2x times 4 plus x, and we got the original expression. If you can expand your result and you get the original expression, then you know that your answer is correct. Here's another example. We need to factorize the given expression. The expression is axy plus 5 plus bx plus cy. And the first thing to do when factorizing an expression is to determine the HCF of its terms. So that's what we're going to do. The HCF of the terms in the given expression can be determined by writing out each term as a product of its prime factors and variables. So axy, the first term, is the same thing as a times x times y. It's a product of variables. 5 as a product of its prime factors and variables. There's no variable here. So 5 is a product of its prime factors. Well, the factors of 5 are just 5. So 5 is a factor of itself, and 5 is a prime number. So expressing 5 as a product of its prime factors is just a simple case of writing 5. We don't need to multiply 5 by anything, because 5 is 5. The next term, bx, same thing as b times x. And cy, the same thing as c times y. So now we need to look for common factors to the expression. So what are the common factors to these terms? Well, a only appears here, x appears here, and here. Y appears here and here. 5 only appears here, b only appears here, and c only appears here. So what we can say is that axy and bx have the common factor x. axy and cy have the common factor y. So what's the next step? Well, now what we can do is group the terms with the same common factor. Now in this case, we know that axy and bx have the common factor of x. So let's group axy and bx in this expression. So this expression is written as axy plus bx as one term plus 5 plus cy. Now factorizing this expression is easy because we know that the HCF of these terms is x. So we divide through by the HCF, and we multiply by the HCF. Then we have this plus 5 plus cy. And this gives x equal x times x and x 1. A times 1 times y is ay. This is 1 divided by, so a times 1 times y is ay divided by 1 gives ay, plus x here 1, x here 1, b times 1 over 1 is b, plus 5 plus cy. So this is the result. But we could have grouped the terms differently. We could have grouped the terms using the common factor y. So we could have, instead of saying, rewriting this expression as this, we could have rewritten this expression as axy plus cy plus 5 plus bx. What we're doing here is we're grouping terms with common factors. Now, axy and cy share a common factor, so we could have grouped them together. Common factor of these two terms is y. So, factorizing this expression is achieved by dividing each term by the HCF. So dividing this expression through by the HCF, and then multiplying the results by the HCF. And this plus 5 plus bx is just written as it is. And simplifying gives y into, well, y here 1, y here 1, y here 1, y here 1. It gives a times x times 1, ax divided by 1, which is ax, plus c times 1 over 1, which is c. And this is the result. So this is one possible result of the factorization, and here's another result, depending on which common factor we group the terms by, but both are correct. Here's a final example question, and says simplify the expression given below. And here's our expression: x plus 2 all squared times 5 divided by 3x plus 6, which can be written as x plus 2 squared times 5 divided by 3x plus 6. Now, if you can see that as it stands, there's nothing we can do to simplify the expression, then you know that something must be done to enable a simplification. Now, if you take this denominator term, 3x plus 6, its terms are 3x and 6. 3x 3 times x, 6 is 2 times 3. As you can see, they have a common, the terms have a common factor of 3. This means that this expression can be factorized. Factorizing 3x plus 6 gives 3x plus 6 divided by 3 divided by 3. You know, you divide through by the HCF and you multiply by the HCF. And this gives 3x plus 3 and 6, 2. 3 into x plus 2. Now, if you write 3x plus 6 as its factorized version, because 3x plus 6 is, in fact, 3 into x plus 2. If you expand this term, this expression, you get 3 times x plus 3 times 2, which is 6. So if we replace 3x plus 6 with its factorized result, we get x plus 2 squared times 5 divided by 3 into x plus 2, which is the same thing as x plus 2 squared times 5 divided by 3 times x plus 2. We can form a fraction with this numerator term and this denominator term, and that fraction is x plus 2 raised to the power of 2 divided by x plus 2. We can also form a fraction with 5 and 3. 5 divided by 3. So as you can see, we've broken down this term into a product of two fractions. And the reason why x plus 2 squared and x plus 2 were grouped together to give a fraction is because they have the same x plus 2 term. And you know from the laws of indices, when you have a term in the form x to the m, or let's say when you use a to the m over a to the n. You can write it as a to the m minus n as a simplification. So x plus 2 all to the power of 2 divided by x plus 2 is the same thing as x plus 2 to the power of 2 minus 1, because this is x plus 2 to the power of 2, this is x plus 2 to the power of 1. All of this times 5 over 3, which is x plus 2 to the power of 1, which is x plus 2, times 5 over 3. X plus 2 is the same thing as x plus 2 over 1. So multiplying these two fractions gives the following fraction. The numerator is x plus 2 times 5, which is x plus 2 times 5. So we can put the 5 here, 5 times x plus 2. And the denominator is 1 times 3, which is 3. Remember, when multiplying fractions, you multiply the result in fraction has a numerator that is a product of the numerators of the original fractions, so x plus 2 times 5. And the denominator of the resultant fraction is a product of the denominators of the original fractions, which in this case is 1 times 3, which is 3. And there we go. The complex expression given, this has been simplified to this.